is really important for insurance. So here you can see this demonstration of property on the slide. Given that X is distributed with Pareto, it is generated at lambda plus W, the shifted second parameter of the Pareto distribution given the conditional probability. And actually there is another way to generate the Pareto distribution, and it can be derived from exponential distribution with parameter 1 and from the gamma distribution. Again, this is the Greek letter gamma, and this is the gamma distribution with parameters alpha and lambda. So using standard methods for transformation of densities, we can obtain that y is the x1 over x2, and this y is the Pareto distributed random variable. The Pareto distribution represents the ratio of exponential and gamma distributions, and because it is just the ratio, it should have the better tail, because these two distributions have thinner tails, and their ratio should give us fatter tail. And generally this property goes from the property of mixture distributions, quite complex things, but you just might understand that you are able to obtain Pareto distribution from exponent and from gamma distribution by just dividing one on another, but exponent distribution should be with parameter 1. Okay, so now let's move on to the task. And this task is about modeling the claim size with certain parameters of Pareto distribution, and we want to calculate the mean sizes of claims greater than 80 and less than 80. Again, you have to look and read very carefully what is stated, not just greater than 80, but this is the conditional property. It is greater than 80 and less than 80. So x, given that x less than or equal to 80, this is just what can be expressed in mathematical way to this text. Okay. Now we have x minus 80 given x more than 80, and this thing can be derived with the Pareto distribution using this property. So look closer at the formula. We have what we have, x minus w given that x more than w, x minus 80 given that x more than 80. So this 80 will go to the shift of the second parameter. What parameter we have here? We have the parameter 360. So 360 will be shifted with this 80, and instead of 360 we will obtain 440, which is exactly 360 plus 80. Okay. So we are using this property to just understand what will be the newly Pareto distributed random variable given that conditional probability. Okay, so let's move to R and just calculate what we see in this example 10. So let's carefully place our formulas and obtain the results of these calculations. First of all, what we can derive initially, x minus 80 given that x more than 80 is Pareto distributed with values of 5 and 440. Okay, so 80 plus 360 is 440. So what will be the expected value of this x minus 80 given x more than 80? We are going to use the formula for our expected value, which is just lambda over alpha minus 1. So lambda over alpha minus 1 is the exact value, which is just 440 divided by alpha is 5 minus 1, 4. So we have this 110 the value of Ex minus 80 given that x larger than 80. So this expected value is 110. Thus, given that we have E of this value is 110, we can obtain the value for Ex given that x more than 80. Okay, and this value is 190, just the sum of those values, 110 plus 80. Next, we know that the probability that x more than 80 is calculated like with gamma over gamma plus w to the power of alpha. Okay, so let's place the formula here. Not the gamma but lambda over lambda plus w and everything to the power of alpha. So we have this kind of formula, and we are ready to find this probability. So it will be 360 over 440 to the power of 5 to the power of 5. We will have 0.36 value, and Ex, our final value Ex, is just 360 divided by 4. Once again we divide by alpha minus 1, and here is 90. So now we're ready to just write the formula for Ex and find what will be the value of Ex less given that x less than or equal to 80. So this is our task. It should be our task. Find this value, x less than or equal to 80. So we are ready to find this value by finding the result of this equality. Ex, first of all, Ex that x more than 80 times probability x more than 80. So we just writing the formula for our Ex, and of course if we have written that x more than 80, we should also write that x less than or equal to 80. X less than or equal to 80, and of course the probability that x less than or equal to 80. So this is our resulting formula, and we must substitute values that we have just defined. First of all, we know that Ex value is 90. We have just derived. Then we know that probability is 0.366. We also know this value Ex, given that x more than 80, this is 190. What else we know? We know this probability of x less than or equal to 80, and we can find this value by knowing the value where x larger than 80. So when x larger than 80, this is 0.36. So if we place all the probability space from 0 to 1, and it can be only filled if x less than or equal to 80 and x more than 80. So we fill all the probability space, and 0.36% goes only to the value where x larger than 80. So the rest values will 1 minus 0.36 will be when x less than or equal to 80. That's it. We already know almost everything except the question for this task. Okay, so just carefully place everything that we have. 90 equals to 190, then 360 over 440 to the power of 5 plus what we need to find x less than or equal to 80 times, and here is 1 minus 360 over 440 to the power of 5. So when we subtract and divide over this value, we can obtain. So let's try to obtain 90 minus this value, 190 times that, and divide by that. So we will have the exact value of 32.11, and this is the expected value of x less than or equal to 80. So once again, how could we obtain? This is the final answer. This is the final answer. How could we obtain those numbers? We were using these particular formulas. So the particular formula which we applied, first of all, we applied this formula that lambda should be shifted with parameter w. Then we have used the formula of Ex, that lambda over alpha minus 1. We also use the formula for the full probability that all events should end up with 1. So if something is less than or equal to, then 1 minus this probability will give us something that is more than x. And we also used this complete probability version, that Ex is just the expected probability times one event plus expected probability times second event. We also placed those things over here in our last formula. This is our last formula. Something times probability, something different times probability. Okay. Then we just have to obtain the only single unknown in this equation that we have successfully done, and the final result is 32.11. Okay, hope you understand what were happening here, and in the next lecture we are going to consider the example for generating and fitting distributions according to particular data, and hope you'll find this interesting. Thanks for watching. See you. Bye.